In this video, we'll look at the relationship between the work done in moving a particle and the electrical potential energy. So imagine nothing exists in the universe except for this one charge. Does its energy depend on its position? If nothing else exists in the universe, there's nothing else to compare its position to. All positions are the same. So, no, it doesn't matter. How much work would be done bringing it from infinitely far away? Well, work is related to force and a change in position. If there's only one thing existing in the universe, force on the object has to be zero. No matter where you move it, there's no work that's being done. So in this case, the energy doesn't depend on its position and no work. We've already brought this particle into this position. What if we bring a second one in? Do you have to do work bringing this one from infinitely far away? Well, now we've got two plus charges. We know the plus charges will repel each other. So if you want this charge to move here next to the other one, then you actually have to push against that force, that electrical force. And so in this case, you would have to do work to bring it to that spot. We've learned about gravitational potential energy. If you have a positive mass, we don't know of anything with a negative mass, so anything at all, going against the direction of gravitational force. So if you're standing on the surface of the Earth, then gravity is pulling down. So you've increased the height of this object with a mass m in the presence of gravity. This makes an increase in the gravitational potential energy. You're fighting against the force. If you have a positive charge going against the direction of the electric field now, that creates an increase in electric potential energy. But in electricity, we have pluses and minuses. If you have a negative charge going with the direction of the electric field, that creates an increase in potential energy. Because remember, in this case, a negative charge, if the electric field is pointing down, the force is pointing up. So again, you're opposing the force. Now what we just talked through, let's see if we can do that mathematically. We're going to just check the sign. So if E is uniform, upward is the positive direction. We know the change in potential energy is minus Q times absolute value E delta X cosine theta. So here I'm just trying to check the sign of these various components. I've brought the negative down. The Q in this case is positive. This is in an absolute value sign, so that is also positive. And the cosine theta, delta x is pointing up, E is pointing down, so it's 180 degrees. Cosine of 180 degrees is -1. So that's a minus. So minus times plus times plus times minus, that has to be a positive. So this should say that in this situation, the change in electric potential energy is positive. Let's try it again with the other situation. Now we've got the electric field pointing down, but a negative charge going down here. So again, the negative is negative. The Q, in this case, is negative, so I'll put a minus in there. Absolute value, so that's positive. Cosine theta. These two are both pointed the same direction, so theta is 0. Cosine of theta is positive. Negative, negative, positive, positive. Multiply those together. You get positive. There's an increase in the electric potential energy.